All right, this is the CS-159 2019 Fall Exam 2. Let's go ahead and get started. All right, which of the following is output generated by the first print statement in the code segment above, or I guess in this case to the side. So our first print statement is this one here, so it looks like we just need to go through these first few lines of code. So let's keep track of our variables here. We'll do x, y, and z, which are 7, 3, and 11 respectively. And then we get to our first statement here. So seeing as they didn't include any parentheses or anything, let's do those ourselves. So if we remember and comes before or, if you look at your precedence table, so we know that grouping, those two statements are grouped together. So if we do x plus plus greater than 7, so that is 7 greater than 7. That is false. 7 is not greater than 7. And since this is false and this is an or statement, then we need to check the other side of the or statement to see if that part of it is true. So then we do y plus plus is greater than 3. 3 is not greater than 3, so this is also false. So since this is false and this is an and statement here, that means this is going to short circuit because nothing anded with 0 is going to be true. So that means this part of it is never going to run. So after this line of code runs, we increment x and we increment y. So x now becomes 8 and y becomes 4. And then we can move on to the next line. So here we do, it looks like we just have one and statement, so we don't really need parentheses. So x plus plus mod 2 equal to 0. So x is 8, so 8 mod 2, that is 0. So 0 does equal 0. So that means this is going to be true. Oh, also, we forgot. In the previous one, our result is just going to be 0, since we said that both of these are false. So this whole thing's false. So result is equal to 0. All right, going back to the second statement. So now we do z plus plus mod 2 is equal to 0. So z is 11. So we do 11 mod 2. That is 1. So 1 is not equal to 0. So this is false. So then we do true and false, which is just false. So we increase this by 0. But in this case, we have to also increment x plus plus and z plus plus. So x increments to 9, z increments to 12. And then our final expression here, we just have an or statement. So we do y plus plus mod 2. So 4 mod 2, that's equal to 0. So this, and 0 does not equal 1. So this means that this is false, or it's 0. And since this is an or statement, we have to check the second part of it. So we do z plus plus mod 2 is equal to 1. So z is 12. So 12 mod 2 is 0. 0 is not equal to 1. So this is 0 again. So result is just going to be 0. So we have to increment y and we have to increment z here since we executed both of those. So y is going to increment to 5, z is going to increment to 13. So then we get to our results section, or our printing here, and the first thing we print is the result, and we said result is 0, so that's going to be A, which is our correct answer. And then moving on to question number 2 here, question number 2 is just asking us what is printed by this statement here. And if you look back on the previous question, if you just joining us, just go back and watch question 1 to see how we calculate it. But at the end of it, x is going to be equal to 9 and y is going to be equal to 5. So if we add those together, we get 14, which is answer C. And then question 3, part of the same code segment we've been working with. So now we're on to here. We're just printing out z. And if we go to question number 1, if you watch the video from question number 1, you'll see that z is 13. So that means this is B, 13. And we can double check that. Yep, 13, so we're good. All right, moving on to question number 4. Which of the following statements regarding logical expressions is false? All right, so part A says, when attempting to print the result of a logical expression that is true as an integer, the result will always be 1. So this is in fact true, so this is not the correct answer. And this is because if we have a statement such as 3 equals to 3, we know that's true. So if you were to print this, this would be 1. Or if you were to do 2 does not equal 3, that's true, so it would print a 1. Any value that's not 0 can be true, but if you're printing a true value, that value is always going to be just a 1. So that's what makes A true. Moving on to B. Complementing a condition is one way to potentially remove negative logic from an expression. So this is true. Might be a little confusing. So if we write a little example here using some negative logic, so if we do if not x, if x is some integer variable, So when we do this not x, that means we're creating negative logic. So if this is the case, we'll do some expression 1. Otherwise, we'll do expression 2. If we want to get rid of this negative logic where we would negate it, we could just take the complement of this expression, which in this case would be pretty simple and would just be if x. And then we would just switch these two expressions here. So this would become expression 2. And then this would become expression 1. So then if x is 1 here, then that means that this statement here would be false. So since we do not 1, that's 0. So then we go to else and we would do expression 2. And then if we had the 1 here and put it down here, then we'd also do expression 2 because it would be true. So we took the complement here, and this removes our negative logic but keeps the same exact logic that we were doing before. So hopefully that kind of makes some sense. And then we'll look at C here, since we have not found our correct answer yet. And C says a logical expression cannot be used as the control expression of a switch construct. This is false, so this is a right answer, because we could have switch x equals 1. In fact, that's what we're probably going to do most of the time. And thus our only cases would be 0 or 1, and we're using a logical expression here. So this is perfectly legal. This is kind of the purpose of switch constructs. So that means that C is in fact our correct answer. All right, question number 5. Which of the following statements regarding the case label of a switch construct is false? A states that the constant expression represented by a case label cannot contain any mathematical operators. So this is in fact false, as it can contain mathematical operators. So if you remember, the case means that it's saying like case 3 or something like that, but we could do like 3 minus 2. I don't entirely know why you'd want to do that because it's kind of pointless. You could just write a 1 instead. But this is legal to do as long as this expression with a mathematical operation, this has to evaluate to a constant. So you can't use some variable here because then that's not legal for switch constructs. So as long as that evaluates to a constant, then that's all right. And then B here, the case label represents an integral type to be compared with the rest of the control expression. This is in fact true. Whenever we have a case like we have here, the label associated with it, which is usually like some sort of number, it has to be of an integer type. So integral type means it has to be like an int, a long, a char, anything that's like an integer that has no decimals. So it has to be of one of these. You can't use floats or doubles with a case label in a switch construct. And then C, no two switch case labels can represent the same constant expression value. This is true. This pops up in a lot of exams. But basically you can't have case 2 like that because they're the same thing. So it would both be pointless, but you also can't do it. So that means A is in fact our correct answer. All right, number 6. Which of the following is the output generated by the first print statement in the code segment? Alrighty, so let's keep track of our 4 variables, x, y, z, and result. So x is going to be 9, y is 8, z is 4, and the result has not been initialized yet. Okay, so first we do this weird looking expression here with 2 greater than signs. So to do that, you have to think about parentheses like that go here. If you were to look at your operator precedence, since it goes left to right. So that means we're doing 9 is greater than 8, which is true. So that's 1, right? Because if it's true, that means it's 1. And then we're saying, is that greater than z? So is 1 greater than 4, which we know is not true. 1 is less than 4. So that gives us a result of 0 initially. So then on the next line, we do this result plus equals. So then we're doing plus equals plus plus x. So that means we need to increment x before we do anything. So we get 10. So we get 10 mod with 4 here. 10 mod 4. And then we're seeing, is that greater than minus minus y? So we need to subtract y before we do anything. So we get z minus minus y, so 7 mod 4. So 7 mod 4 is 3. 10 mod 4 is 2. So is 2 greater than 3? No, it is not. So that means our result is 0. And we did nothing to change z in this expression. And then if we move on to our next line, we do another plus plus x. So we need to increment x first. And then we do a minus minus y as well. So we need to do subtract that to 6. So then we get 11 mod 4 is greater than 6 mod 4. So that is just 3 is greater than 2, which is true. So that means we increment result by 1. So then we print out our first result, and result 1 is just 1. All right, question 7 here. So if we'll just carry over our previous x, y, and z values and result from the previous question. So x was 11, y was 6, z was 4, and our result's going to get reinitialized, so it doesn't matter what we put here yet. So if you're confused on how we got these, just go back and watch the explanation for question number 6. As I talk a little bit more about how we got these values. So that means we're starting on this line here, as we already executed all this stuff. So that means we start with this x plus plus. So we do that. It means we increment afterwards. So 11 does not equal, and then this is effectively in parentheses due to order precedence. And we have a plus plus z here. So that means z is going to increment to 5. And we're going to do 6 plus 5, so we get 11. And so we're saying 11 does not equal 11, which is false. So that means result is now going to be, result is going to be 0. So then if we move on to our next line, we also need to remember we need to increment x plus plus. So x now becomes 12. All right, so then before we start this next line, we need to do x we need to do plus plus x again. So that means x becomes 13. So then we're doing 13 does not equal, and then we have y plus z, so 6 plus 5, and then that'll get incremented. So 13 does not equal 11, which is true. So that means the result is going to be 1, and then after that we have to increment z by 1 to get 6. And then moving on to the next line, we have a bunch of ands here. So the way this is going to work is we're going to and that, and then it's going to and with this whole thing here. So first we're going to do x and y, I believe. So we get 13 and 6, and those are both true values. So that means that this is just going to be a 1. So then we get 1 anded with z mod 2. This should be all the way over here. Z mod 2 equals 0. And so z is 6. 6 mod 2 is equal to 0, so this is also true. So that means we have 1 and 1, which is 1. So we're increasing result by 1 to get 2. So that means this result is just going to be 2. All right, question number 8. Which of the following statements regarding selection constructs is false? The first one states the conditional expression has 3 operands and a 2-token operator. Okay, so this is going to be true, actually. It's not going to be false. So the reason this may be a little confusing, you may not understand exactly what the conditional expression is. When I first read it, I thought it was a logical expression. But what this is also known as is the ternary operator. So the ternary operator, if you remember correctly, is the thing with the question mark and then the colon. So we'll have some logical expression here, then we'll have a question mark, and then we'll have what gets executed if it's true, and then what gets executed if it's false. So it's basically an if statement, but in one line. So if we see here, we have 3 operands. These are all operands. The logical expression, and then what we do if it's true, and what we do if it's false. And then we have two operators. So a 2-token operator, which is this and this. So that makes A true. So B, we'll check out what B is. It says the short circuit method of evaluating logical expressions is not applicable to logical expressions of an if-else construct. This is false. So this is the correct answer, because this is very much, short circuits are very much applicable. Anytime we do any sort of logical expressions, short circuits should be considered as anytime you have a logical expression, a short circuit can occur. And then we'll just verify C. The logical expression of an if-else construct requires an enclosure in parentheses. This is true. So basically what this is saying is if we have if statement, we can't do if x equals 2 like this. It has to be if x equals 2 with parentheses around it. So that is false, so that means B is in fact our correct answer. All right, question number 9. Which of the following statements regarding repetitive processes is true? Okay. So in an event-controlled process, we know the total number of times that the actions found inside the body of the loop will be executed. This is false. This is describing a counter-control process. A counter-control process knows the number of times. An event-controlled just ends whenever a certain event occurs. So that's false. B, according to core standards, the use of a for loop must be limited to event-controlled processes. This is false also, as it's backwards, as for loops should be used for counter-controlled processes, and while loops should be used for event-controlled processes. And then C, while the concept of recursion is not limited to pretest or post-test, it is poor design to use it with event-controlled processes. This is true. So an event-controlled process is when like a certain thing happens. So say we use recursion on input validation, for example. So we would have to check if is the number in a certain range, and so it only ends when a certain event happens, and that's when they input it in the correct range. But say they input the incorrect range like a million times in a row, then our recursion tree is going to get really, really, really long because we're going to have a lot of recursive calls, and this can result in a Stack Overflow because we run out of space in our computer because we have so many recursive calls. So you should actually use recursion with more like counter type controlled processes where we know how many times it's actually going to execute. So that means C is our correct answer. All right, number 10. Which of the following statements regarding looping constructs is false? A, immediately following the update action of a for loop will be the evaluation of a loop control expression. This is actually true. Because the way this works is, so we have our for loop. So if we have a for loop down here with all of the stuff in here, then we have our body. This is our body down here. The way it's going to work is that we're gonna execute the code in the body. Well, first we have to initialize everything and then check, make sure it's in the bounds. But then after that, while we're looping, we do the body, and then after we do the body, we increment it. So usually we do like I++. So that's when we increment it, and then we check our condition, which say it's like I is less than 2. So that means that the thing that immediately follows our update action. Sorry, this is our update action. The thing that immediately follows is evaluation of our loop control expression. We don't execute any body or anything, so that makes this true. And then B, the initialization of the loop control variable must take place outside of the body of a do-while loop. This is false, because this is kind of the purpose of a do-while loop, as it'll say we have like a variable x here. We don't have to initialize it until inside of the loop. So say x is less than 2. Sorry for the bad handwriting. Because we can enter this loop because we're not evaluating anything, so we can initialize it inside of here. This isn't a very good loop, but this just shows you that we don't have to initialize it outside of the body of the loop due to the way a do-while loop works. If this was a while loop, on the other hand, then we would have to initialize it. Otherwise, we would be checking this expression first, and x would be uninitialized, which would be problematic. C, in a while loop, the number of times the loop control expression is evaluated is one more than the number of times the loop will iterate. This is true because every time we loop through, eventually it'll become false, and then we'll have to actually check the expression to see is it false, and then we know it is false, so then we break out of it, but we don't actually do anything in the body of the loop. So that means we end up executing the loop control expression one more time than the loop body itself. All right. And so that means that B is our correct answer. So 11 is asking us to trace through this code and see what is printed by the print statement at the bottom of the program. So if we, we'll write down all of our variables here. So we have x, y, let's move these over a little bit. We have x, y, z, I guess we have a w too. So we'll move all those over here. And then we can start tracing through all of this code to see exactly what it is doing. So w is going to be 0, x is 5, y is 10, z is 0. So here we have an expression, and remember and comes before or. So these ands are going to be executed before this or statement. So we do w and x, so we have 0 and 5. And anytime we do 0 in an and loop, or in an and, that means that it's going to be false. So this is 0. And since we have an OR, we need to check what the other part of the OR is since the first part was 0. So then we do 10, which is true, and Z, which is 0, which is going to be false. So these are both false, so that means we don't do this one, and we move on to this next else if. So then if we remember, and comes before OR again. So then we do not W, so 1, and not X, so 0. And 1 and 0 is false, so that means we need to check out the next part of the OR, which is over on the right side. So then we do not Y, which is going to be 0, and we do not Z, so not of 1. 0 is going to be 1, so we have 0 and 1, although I guess we didn't need to do that technically because this will short circuit since this is an and this is 0, so that means that we're also not going to execute this. So then we'll move on to the next else if. So then, and before OR, so we have those. So we do the first part of this OR, so we do not W, so we get 1. And since these are all ORs, or since this is an OR with the rest of this, that means that this is just going to be true, and that these are just not going to get executed because we don't care about what happens to them, since we know that it's going to be true no matter what since it's an OR. So that means our Y is going to change to a 1. So if we look at our correct answers here, that means B is going to be our correct answer. All right, number 12 is looking at the same code segment that we were looking at before. So but this time we're talking about the complements of these logical expressions that we have. So line 14, this is going to be line 10, this will be line 14, and then this will be line 18. Okay, so this is kind of a tough question to figure out, as it's asking us about 3 different ones and 3 different logical expressions effectively, and if any of them are complements with each other. But it's hard to check that because there's 4 different variables, which means there's 16 possible enumerations of 1s and 0s. So let's just take this one by one. So if we look at lines 10 versus lines 14, we'll see that if X and Y are different, then that means that these are not going to be logical complements. So a counterexample, just so you have it for all of these. So the correct answer is none of the above. So a counterexample that shows that it is in fact none of the above is X, Y, Z, and W. If you do 0, 1, 1, and 0, all of these are going to have the same exact value for this expression, which is going to be true, I think. So all of these will be true if you put in X, Y, and Z, and W and with these values. So that proves that they are all, in fact, not complements, because complements mean they have to be different results for every single combination of X, Y, and Z's. So in this first one up here, between lines 10 and 14, for them to show that they are not complements, we can show that X and Y just have to be different variables. So say X is 1 here, and Y is 0. So then down here, that means X is going to be 0, and Y is going to be 1. So then we can effectively choose any W or Z, because this will get executed first here. So we know that this is never going to be true here. And then this one over here, if we say Z is perhaps, I don't know, we could say Z is 0, so then this is 1. That makes this true. And then we know that this is going to be false. And then all we have to do is make W true. So that means this is true and this is true. So these are not complements because they're both true. So this is definitely a really tough problem. It's a tough problem to kind of explain too. But pretty much it boils down to you have to just mess around with all of these and see if you can figure out values of X, Y, and Z that make it so that they're not complements of each other. So you have to find counterexamples. So then if we look between 14 and 18 here, if we have X equal 1 and W equal to 0, then these two could have the same result, primarily because they both have not W, but then right after it, this is an and this is an or. And then, so this is always, if you make this W a 0, this is always going to be true the rest of the way. And then, so then, if W is a 0 up here, that means this is 1. And so all we have to do to make this entire expression true is make, actually, I think X has to be 0 here, sorry, not 1. So then if X is 0, this is going to be 1. And since there's an or here, that means this entire expression is true. And we already showed that this expression is true, so they'd both be true. So they wouldn't be complements of each other. So then if we're looking between 10 and 18, w and x, if we say like w and x are both 0 again, so w equals 0 and x equals 0, then that means that, let's use a different color. That means that this expression here would be false. But down here, this would be true. And then, so this entire expression would be true. So I guess, yeah, our x value doesn't really matter for this one, but that's all right. So then all we have to do to make these complements of each other is make y and z true. So we just make those both 1s, and then these become not complements of each other because they have the same result. Okay, so it's kind of taking a little bit to get to this point, but basically a good way to go about seeing it is, especially with line 18 here, with line 18 we have this or here, and we have this not w immediately before it, so it's really easy to make this whole expression true if we just make this a 0. So then if we want to prove that this is not a complement with another one of these, we just have to try and make this entire expression true when w is equal to 0. So when w is equal to 0, we know that this expression can't be true because this is a 0 and we're anding it. So we have to make both of these 1s to make it true. Since it's an or, so the entire thing will be true. So these will both be complements of each other. And likewise for 18 and 14 here, like we said, if we make w 0, then this is true. And then we just need to try and make this true with w 0. So we have a 1 here, and then we can just make x a 0 to make this a 1, and we're oring it, so that means this entire expression is true. So that's kind of probably the best way, is to figure out these kind of things where it's just like one variable that we need to change to make an entire expression true, and then try and use that same variable in the other ones, and then try and make the expressions true using the rest of the variables. So basically you just have to prove it by counterexample. That's to prove that none of them are complements. If they are actually complements, then this would be really hard, because we'd have to enumerate pretty much all the possibilities. So eventually we figure out here that it is D, none of the above, as none of these are complements of each other. Alrighty, number 13. Which of the following statements regarding the for loop construct is true? A, the use of either x++ or ++x are interchangeable as the update expression for a for loop to increment the loop control variable. This is true. Oh my goodness, whoops. Sorry. All right, so this is true because it doesn't really matter if we use I++ or ++i at the end. So this is saying if we have this for loop, I is less than 3, we do I++. It's saying, do we need to do I++ or ++i here? And either one works. They work the exact same, because the way this gets executed is we do the body, and then we do the loop control expression by itself. So this always gets executed after the body, no matter if we use the postfix or the prefix. So then let's just check our other answers. B, it is not possible to update the loop control variable of a for loop inside of a body. This is false. It's not very good practice to do this, but you could do for I equals 0, I is less than 3, I++, and then inside of our loop we could do I++. So this would be kind of a weird one to trace through, but it is perfectly valid. We can update the loop control variable inside of a for loop. This is definitely against course standards though, I think, but it is possible in the C language to do this. C, the compiler used as our server on our server for the semester, in this case was Vocarium, will permit a variable to be declared and initialized in the first expression of a for loop. This is false. If you ever try this, what this is saying is can you do this? For in I equals 0, I is less than 3, I++, instead of doing like this expression here, where we do in I and then use it. So if you ever try to do this bottom one here, try putting it in, it'll throw an error at you, because it doesn't like you initializing the variable right here. So make sure you do it like this. So that means A is in fact our correct answer. All right, number 14. Which of the following would not be a violation of course programming standards? A, making use of a for loop but not using all three of its expressions. This is a violation. So we can't do something like for I equals 0, I less than 2, and then just don't include the last one. That would be a violation. So you have to always include all three parts. So we need to make sure we include our incrementer at the end of it too. B, we cannot use break to terminate a loop. I know lots of people want to do this in this course, but it's against course standards. So if you're in a while loop or a for loop, you can't use break. And then C, allowing a single user-defined function to terminate in multiple places through the use of multiple return statements. This is also a violation, as you can't have multiple returns in a user-defined function. So that means D is our correct answer. All right, number 15. Which of the following is the output generated by the first print statement in the program? Alrighty, so the first print statement is just going to be this code right here. So for now, we can ignore all of this stuff since we don't really need it. So let's trace through it. So leap 1, we pass a 1900 into it. So to make our lives much easier, let's make, so this entire, it looks like we're only using leap 1. Leap 1, leap 1, leap 1. So we don't really care about these other user-defined functions right now, so we can kind of just ignore them. So we have this very yummy ternary expression here. We have 2 question marks, which means we have 2 ternary operators. So let's break this up into a standard if-else to kind of get a better feel for it. So this is the first condition of our if. So we do if year mod 4, and then our true expression is just 0 here. So that means since we just have a return here, that means we would just be returning 0. So then the second, our false part of this if is all of this stuff in parentheses here. So that means we do else, and then we have, we have else, and then so we have a nested ternary operator inside of here. So we have our logical expression here before the question mark. So that means that the if inside would be if not year mod 100 and not year, run out of room, mod 400. So if that's the case, then we do our true statement, which is 1, so we would just return 1. Otherwise, we're doing our false, which is returning 0. Okay, I guess we'll make that the same color as up there. So now we have our 1900 that we passed into here. So that's our year. So we do 1900 mod 4, which is 0. So that means our else is we're gonna go into our else statement. So then we're gonna do 1900 mod 100. 1900 minus, or mod 100 is 0, right? Because there's no remainder. So that means we have a 0, but then we not it. So this is a 1. And then we do 1900 mod 400, which is, what is that, 300 or so? Yeah, 300. So that's going to be 300. Basically, it's going to be greater than 0. So we have 300. So this, when we not it, that means this is going to be 0, which means this whole expression is going to be false, which means that we're going to return 0. So that means this first one returns 0. So now we got to do, we're going to erase all of this, and we're going to do 2000 for our year. So 2000 mod 4 is also 0, so then we need to go into our else statement. So then we do 2000 mod 100, which is 0, and we not that, so that means this is 1 here. Then on the right side we do 2000 mod 400, which is also 0. So that means that we're going to have another, since we not it, we have another 1, which means this is all true, which means we return a 1. All right, and then we'll check out our last one. This one we pass in 2020. So 2020 mod 4 is also 0. So we go into our else again. So then we check in here, 2020 mod 100, that is going to be 20. So not of 20 is 0. And since this is an and, we don't need to worry about the second part. So that means that this is going to be false. So we do our else and we return 0. So that means leap 1 is going to be the sum of those, which is just 1. Alrighty, question number 16. We're looking at the same piece of code here that we were working with before. This time we only care about this part, so that means we can ignore all this, and we're only using leap 2, so we can ignore this and ignore this. So let's do what we did last time for 15, and let's write out what this massive ternary expression would be in terms of if and else's. So this means this first expression here this is all part of our if expression. So we'd have if not year mod 100 and not year mod 400. So then if that's true, then we just return 1. Otherwise, we're going to do this ternary expression here, which is going to be, so we'll do else, and then it's going to be, our if is just going to be if not year mod 4. We'll return a 1 here. Otherwise, we're just returning a 0, which is right here. Okay, and then we'll put our closing one. So then let's put some values into here. So we're passing in 1900 for the first value. So that means we're doing 1900 mod 100, which as we said before is 0. So that means that this is going to be true. And then 1900 mod 400 is not 0. So that means that this is going to be false, because it's going to be 300, not 300 is 0. So then we go into our else here. So then we do if not year mod 4, year mod 4. So 1900 mod 4 is 0. Not with that is 1, so that means that we do this. So we return 1. So that'll be a 1. And now we will do a 2000. So we do 2000 mod 100, which is 0. Knotted is 1. Then we do 2000 mod 400, which is 0. Knotted, that means that this is 1. So we have 1 and 1, so that means that we're just going to return 1. And then we do 2020. So we do 2020 mod 100, that is 0. Nope, just kidding, that is not 0, that is 20. So then we do a not of 20, which that is 0. And nothing ANDed with 0 can be true, so that means that this whole expression here is false. So we go into our else. So then we do not 2020 mod 4, 2020 mod 4 is 0. Knotted is 1, so this is 1, 1. So then we return 1 for the last one too, so we sum all those up and we get 3. So our correct answer is C, 3. Number 17, same code statement we've been dealing with here, last one. So we don't care about this, we don't care about this since we're reinitializing leap. And then we're using leap 3, so we don't need those and we don't need that one either. So then leap 3, we pass in 1900. But before we do that, let's do what we've been doing with our ternary, because this time we have 3 ternary operators, which gets kind of nasty. So our first one, this is our that's our condition. Then if it's true, we do this. Nope, not just that. We do this whole thing all in these parentheses. And then if it's false, we do this. So that means we get if year mod 400. If that's the case, then what do? We do this entire inside body here. So this inside body is going to consist of another ternary, where that's the logical expression, and then this is the true, and then this is the false. So that means we're going to have if year mod 100. If that's true, then get this, we have another ternary operator. How fun is this? So then we have another one. So this is the if statement for that one, and then this is true, and then this is false. So then inside of this we have if year mod 4. Then if that is finally true, then we just do 0. So we return 0. If it's false, we return 1. Let's line up these colors. So then we're getting back to the else of this blue one, which we said was 0 here. So if this else gets executed, we just return 0. And then finally, on the big outside one, we have this 1 that we return if that one is false. So this is how I'd recommend kind of breaking these ternaries down, is kind of all these lines I drew here helps you visualize when you have all these things embedded inside of each other. Just, highlight the big true and false statements, and then try and write it out in terms of if and else's, as it helps you kind of see how it works a lot easier than trying to do it all in this one ternary expression. So then the first one we pass in is 1900. So 1900 mod 400 is going to be not 0. It's going to be like 300. So that means that is true. So we go into this next one. So then if 1900 mod 100, 1900 mod 100 is 0, so that means that's going to be false. So that means we're going to return 0 here, because that's the one we end up in. So we return 0, so this is 0. So then if we move on to our next one, we're passing in 2000. 2000 mod 400 is 0, so we just jump all the way down to this last else statement and return 1. And then our final one here, we put in 2020. 2020 mod 400 is going to be 20, I believe. So that's going to be true. So then we move down into this one, 2020 mod 100 is also going to be 20. So that's going to be true. So we move down into this one, 2020 mod 4 is going to be 0. So that means we go to our else statement here, so we return a 1. So then we sum all those up, store it into leap, so we get leap is 2. Leap 3 is 2. So C is our correct answer. All right, number 18. Which of the following is the output generated by the first print statement in the program? So our first print statement is right here, and it's just passing in a 10 into days mo, and then printing that out effectively. So if we track through here, we'll just make a little variable for our days, because that's going to be the one to keep track of. So days is going to be 0. So we're switching on 10. So that means we skip all the way down until 10, which is right here. So we start right there. So we do 10, nothing happens, and there's no break. So we filter to the next one. So 12, we do days plus equal 1. So days becomes 1. Then we filter because there's no break. Nothing happens. Filter because there's no break. We do days plus equals 30. So we get 31. And then we filter. But now we have a break. So then we jump out all the way to the end, and then we return days. So we print out 31 here. So it means C is our correct answer. All right, 19. Now we're passing in 11 into days mo. So we'll keep track of our days again. Our day starts at 0. So we'll go down to 11, which happens right here. So then here we do days minus equals 1. So this becomes -1. Then we go here, nothing happens. Nothing happens all the way until here. We haven't hit any breaks, so we keep going down. Then we do days plus equals to 31, so we get days is 30. And then we are done, so we break out of there and we return days, so days is 30, so result 2 is 30. And then 20, we pass in a 2 here. We have days, we'll keep track of that. Days starts at 0. 2, that's our first case here. So we do minus equals 3, so minus 3. Filter, nothing happens, keep going. And now we're on case 12, where something finally happens. We do days plus equal 1. So we get -2. Then we filter 6. Now we do days plus equal 30, so we get 28. 28. And then we filter, but now we break. So we break out of here, return days, which is 28. So we get none of the above, because it's supposed to be 28. All right, number 21. Which of the following is output generated by the print statement in the code segment? Okay, so this one, we are just going to have our variable here, which is just x. So x starts out at 520463. So I'm also just going to keep track of x mod 2. This isn't stored anywhere, so we'll use a different color, but this will just help us kind of see the progression of this. So when we mod this huge number by 2, you might be thinking to yourself, how do I divide that by 2? Well, in this case, we just need to check, is this last number divisible by 2 or not? If it is divisible by 2, then this is 0. If it's not divisible by 2, then it's 1, right? Because if it's not divisible by 2, then in this case, 3 mod 2 is 1. So in this case, x mod 2 is 1. So that means that this is still true. So then inside of it, we divide x by 10. So we get 52046. And then we increase it by 1. So we get 52047. So then we'll do x mod 2 again, because we loop back up to the top. And 7 mod 2 is just 1 still. So then we divide by 10, and then we increase by 1. 5 mod 2, well, that is 1 again. So then we keep going through our loop. We get 520, increase by 1, we get 521. 521 mod 2 is still 1, so we keep looping. We get 52. Then we get increase by 1 to get 53. 53 mod 2 is going to be 1 again. So then we divide by 10, we get 5. Then we increase by 1, we get 6. And finally, x mod 2, in this case, is going to be 0. So this is false, so we break out of it. And we print out our final x, which is 6. All right, number 22 now. So we're looking at the same code segment as number 21, but now we have a new x value. So this new x value is it's going to be 826,049. And then we're going to keep track of x mod 2 again to help us out. So if we remember our little trick, we'll just do, we know that x mod 2, we just have to look at the last digit, so 9 mod 2, that's 1. So then we divide by 10 and increase by 1. So if we divide by 10, we get 82604. So we will increase at 82604, increase by 1. That mod 2 is 1, so we divide by 10 again. These are really bad numbers, sorry. 8260. Then we increase by 1. 8261. Then we mod that by 2 again, still 1. So we keep looping. Then we get 826. Increase by 1, 827. Divide or mod by 2 is still 1, so we keep looping. We get 82, then 83. Mod 2, still 1, so we keep looping. We get 8, then we get 9, still 1, so we keep looping. So now we divide by 10. 9 divided by 10 is 0. Then we get 1. We increase, we get 1. So then this is still 1, so we keep looping. Divide 1 by 10, we get 0. Increase by 1, we get 1. 1. Well, I think we're stuck in an infinite loop here, right? Because we're always going to be 0. Then we'll increase to 1, and that's always going to be mod 10, or mod 2 is going to be 1, and we divide by 10. And then this, we're just going to get stuck in a loop of 0, 1, 0, 1, 0, 1, 0, 1, like that. So that means that this is just an infinite loop. So this is actually none of the above, because we get stuck in an infinite loop right here, so we never actually make it to this print statement, so nothing actually gets printed out. So that's our correct answer. So if you actually try and run this code on boiler exams, you'll see that it'll probably tell you that no output is printed. But if you were to put a print statement inside of the infinite loop, then you'll just see it print out 0 and 1 a bunch of times, because it's just an infinite loop. All right, number 23, looking at a new code segment here. So we have x and y, which are 99 and 22. And then we're also going to keep track of a few other things that aren't stored anywhere, but just worth keeping track, which is x plus y, and then also x mod y, just so we can see the progression. Let's move this over a little bit. And then we also have this variable target. So target is initially 1. So x plus y mod 2. So x plus y is going to be 121. So 121 mod 2 is 1. So it does not equal 0, so we do this else. So that means we increase y by 1. So we get 23. So we go from there to there. So then we check x mod y. So 99 mod 23. I have to do a little bit of math, but that's going to be 7, I believe. 7. So then that is true, so because 7 is greater than 1. So now we're going to loop again. So now we do x plus y, which is going to be 99 plus 23, which will be just 122. Mod 2, that time this is going to be equal to 0. So then we'll go into this if statement here. So we do x minus minus, so we go to 98. So now we have 98, and we're right here. So then we have to do x mod y again. So 98 mod 23 is going to be 6. So 6 is still greater than 1. So that means we keep looping through. So now we do x plus y again. X plus y is now going to be 123. And 123 mod 2 is equal to 1. So we go into our else. Oh, on that loop before, we were in here, and we went to here. I realized I mislabeled that. But it's still correct what we have so far. Okay, so we're into this else statement, so that means we did increase y to 24. Then we do 98 mod 24, which is going to be 2. And that 2 is greater than 1, so we loop one more time. So then we do x plus y, 98 plus 24 is 124. And then, 98 plus 24. Is that? Yeah, that's 124. Is it? No, it is not. Whoops. That's 122. I think we forgot how to do math here, because that is also, this is going to be 121. It should be alternating between 121 and 122. All right, sorry. That doesn't change our answer still, because 123 and 122 mod 2 are both the same, so it doesn't change our answer. So 122 mod 2, that is going to be equal to 0. So that means we're going to do x minus minus, so we'll get 97. So now we do 97 mod 24. And finally we get something that's 1. And 1 is not greater than 1. So that means we break out of this loop and we can print out our final values of x and y. X and y are going to be 97 and 24, which is B. All right, moving on to number 24. We have our same code segment that we were just dealing with, but now we have some new values. So we're going to have x and y again, and we're also going to keep track of x plus y and x mod y. And then we also have our target value. So x is 10, y is 10, and our target value is 1. So first we do x plus y mod 10. So that means this is going to be 20. 20 mod 2 is going to be 0. So that means that this is going to be true, so we just decrease x by 1. So we get 9. And then we do 9 mod 10, which is just going to be 9. And 9 is greater than 1, so we're going to loop through again. So then we're going to do 10 plus 9 again. So we'll do 10 plus 9, and then we'll mod by 2. So 19 mod 2. We'll write 19 there. 19 mod 2 is 1, so that means we go into our else, because 1 is not equal to 0. So we increase y by 1. So then we do x mod y. So we do x mod y, 9 mod 11, which is just going to be 9. And that is greater than 1, so that means we're just going to loop through again. So we're going to notice a little pattern here, because these are just going to alternate between increasing and decreasing. X and y are going to alternate between increasing and decreasing. And since y is increasing and x is decreasing, x is going from 10 downwards because we're doing x minus minus, and y is increasing. That means since we're already at a point where not x is less than y, that means anytime we do this x mod y, that means the result is always just going to be x. So this is effectively just saying, well, x is greater than target. So what we could do instead now is we could just go through and we could alternate increasing and decreasing x and y until we find x is equal to 1. So if we do that, then we'll do, so the last thing we just did was increment y by 1. So now we'll decrease, and then we'll increase, decrease, increase, decrease, increase, decrease. Oh, I did not increase that. Increase, and we'll just keep doing this until x is equal to 1, because that means we'll break out of our loop. So 3, 17, 2, 18, and 1. So now x is 1, so that means we'll be doing 1 mod 18, which is just 1, which is not greater than 1. So we break out of our loop. So as you can see here, we could have traced through this the entire time, but that would have taken a while. So instead, we notice this trend, and we kind of get a feel for how it's working, and we can pick up on it and realize that B is our correct answer. So if that doesn't make entire sense to you, just trace through it, and you'll see this pattern emerge where this x is just decreasing and this y is just increasing, and since y is always bigger than x, this x mod y is just equal to x. So we just need to find when x is greater, or it's less than or equal to the target, and then it'll break like we did here. Okay, moving on to question number 25. We have a new looking code segment here. So the first thing we're doing is finding just total. So we don't really care about total 2 right now. So we're going to pass a 50 into here and a 1 into the option thing here. Okay, so that means we're doing this for loop. So we do for I equals x divided by 2. So that means we're doing I equals 25 while I is greater than or equal to 1 and I minus minus I. Okay, so if we're doing that, let's give this a trace through and see if we can get the correct answer. Okay, so this first expression that we have here is we're just doing 50 mod I. So in this case, I is just going to be 25. And we're going to see, is that equal to 0? And if it is, then we jump into this switch statement. So we'll do switch of 1. So since we're doing option 1, that effectively just means that this right here is just going to be doing total plus equal I. So we can kind of ignore all of this and just write it as total plus equals I, like so. So basically, anytime 50 mod I So anytime we find a divisor of 50, then, because that's what it means when it equals 0, every time we find a divisor, then we increase the total by that divisor. So and we start at 25 and we go down to 1. So we know 25 is a divisor, so that means if we keep track of total here, we're going to start with 25, because it was 0, and 25 is the first one we start with, and that's a divisor. So then the next divisor, if we think about it and we go all the way down through all of the different divisors, the next divisor is going to be 10, I believe, right? Because 24, 23, 22, 21, 20, 19, 18, 17, 16, none of those are divisors. So our next one is 10. So we'll increase, because x mod 10, 50 mod 10 is going to be 0, because 10 times 5 is 50. So that means we increase total by 10, so we get 35. So then our next divisor is going to be 5, if we keep going down. So that means this is going to be 40. Then our next divisor for 50 is going to be 2. 50 divided by 2 is 25, so this is going to be 42. Then our last one's going to be 1, and since this is I is greater than or equal to 1, this is going to, 50 mod 1 is going to happen. So 50 mod 1, of course, is 0. So that means this is 43. And then after that, our loop breaks, so then we return the total, which is 43. All right, number 26, we're dealing with the same thing. However, this time we're doing option 2. So I is still starting at 25, but this time we're just doing total plus plus, right? Because if we do 2 here, that means we're doing case 2, so total plus, well, that's a terrible plus, plus plus. So basically all this is doing, like we talked about in question 25, since we're just doing x mod I equal to 0, that's just finding is the number divisible by, is 50 divisible by I. So we're finding all of the divisors between 25 and 1 for it. So we just need to count the number, and we kind of did that before, but so we have 25, then our next one is 10, then 5, then 2, then 1, because 1 times 50, but 50 is outside the range, but 1 times 50 is 50, 2 times 50, and 5 times 50. So that means we have a total of 1, 2, 3, 4, 5 divisors, and so we'll increase total 5 times. So that means total 2 is going to be 5. All right, which of the following statements regarding the make total function in the program is false? Okay, so I bet what we were just talking about will kind of help us out in this. So it says when opt is 2, the value returned in the number of factors of the, oh, this is a typo. This should be is, I think. When opt is 2, the value returned is the number of factors of the integer x. So that means option is 2. So we have a 2 here. So that means this doesn't happen. So we're just doing total plus plus. So like we talked about, this is the number of factors of our integer, right? Because even though we're starting at x divided by 2, this actually still works because anything that's greater than x divided by 2 is impossible for it to be divisible, right? Because we can't do like anything between 26 and 49 is not, 50 is not going to be divisible by any of those. It'll only be divisible with like a decimal number, since 2 is the smallest possible integer that it could be divisible with. So that means that A is in fact true, so that's not going to be our correct answer. So then we'll look at B. When the opt is 2 and the value returned is 0, then the integer x must be prime. So we might think that this is true because it's finding the number of factors, but it's also saying 1 is a factor, right? So if we look back at our code from 26 here, we said that 1, since we go greater than or equal to 1, that means 1 is going to be one of our factors. So in that case, this is not true because it's saying the value returned is 0. So let's just put in a prime number, for example. So if we pass in 13 here for x, then that means we're going to start at I equals x divided by 2. So 13 divided by 2, integer division is 6. So we start at I equals 6, and we go down to 1. So obviously nothing between 6 and 2 is going to be divisible, as 13 is going to be divisible by, since it's prime. However, we do get to I equals 1 at some point. And 13 mod 1 is 0, so we're going to increase total by 1 and return 1. So this B is false, which makes it our correct answer, since it's going to return a 1. And then just to be safe, we'll check C as well. C says when opt is 1, the value returned is the sum of the factors of the integer x. So when we have 1 here, So this is basically just question 25, I believe. So if we look at question 25 here, we just summed all of the factors between it, because this is going to be 25, 10, 5, 2, 1. So we just summed all of the factors of the number 50, not including 50. So that means that this is in fact true, which makes it not a correct answer. Alrighty, number 28, moving on to number 28, we have a bit of a long code type question here. So let's go ahead and jump right into it. So it looks like we have a little bit of pass by address too, so we'll want to be careful of that, because that can make it a little bit more complicated. So in our main function here, we have x, we have iterations, which I'm just going to abbreviate to be that, and we have our total. So x can be 4, it's going to be a pretty big number here, so it's going to be 4, 6, 5, 8, 1, 7, 2, iteration 0, and total is going to be 0. So then every time we call this make total, and then we divide x by some number. So let's check out what our make total function is going to be doing. So if we keep track of an iteration of it, we have x and we have count. And since we're passing by address, these two variables are going to be linked, iterations and count. So anytime we increase count, we have to increase iterations. So let's be mindful of that. And then we also have some total in here. This x and total are unrelated to the ones in main, because they're not being passed by address. So x is the same because we passed this value in, and then total is also going to be 0. And then for our count variable, it's going to start at 0 because it's linked with iterations. Whoops. So we're saying while x is greater than 0, then we do all this stuff. Alrighty. So let's take a look through it. So the first thing that we do is we increase our count by 1. So we increase this, so increase this to 1. So that means iteration is also going to increase by 1, right? So then we do total plus equals x mod 10. So then we just basically take off the last digit and just add it to our total. So we get 2 here. And then we're saying if x mod 2 is equal to 0, then we divide it by 10. And in this case, it is equal to 0 because we have a 2 at the end. So we get 4, 6, 5, 5, 8, 1, 7. And then we divide by 10 again. So we get 4, 6, 5, 8, 1. So then we increase our count by 1 to get 2. So we increase iterations by 2, or by 1. Then we add the last digit to total. We get 3. Then this mod 2 is not equal to 0, so we don't do it twice. So we just do it once. We do 4, 6, 5, 8. And then we increase our count by 1 to 3, which increases iterations to 3. And then our total now becomes, we add the 8 to it, so now it becomes 11. And then 8 mod 2 is 0, so we have to divide it by 10 twice. So then we get 4, 6, 5, and then we get 4, 6. And then we increase our count by 1, since we're still greater than 0, which increases this by 1. And then we add this digit over here, so we get 17. And then we have to do x, we check x mod 2, it is 0, so then we divide it by 10 twice. So we get 4, and then we get 0. So finally, we break out of this loop, and we return our total. So our total plus equal, we get 17 up here, and our iterations is 4. So we're just going to erase all this so it doesn't get too long. But our iterations is 4, since we passed that in by address. Okay, cool. So now we have to do x divided by equal times this power. So this is going to be 10. And so iterations mod 4. So we do 4 mod 4, which is 0. So we just divide it by 10. So this is just going to be 10. So we only get to divide this by 10, which is kind of not fun, right? Because we just saw how long that loop down here took before. But now we have a better idea of how that loop down there works, so we can kind of run through it a little bit faster. So let's delete all of this down here. So our count is going to be 4, right? Because we pass it in down here. And then our total is going to be 0, because we initialized total right there. Okay, so let's loop through this again. So we increment our count, then we add the last digit to total, and then since this isn't divisible, so basically anytime this is divisible by 2, we divide by 100, otherwise we divide by just 10. So we're going to say that so then we can speed this up. So then this is that. Okay, so now we increment our count. But we incremented too many? Nope, we're good. Okay, increment our count. And now our total becomes 8 because we add by 1. So then this becomes 4, 6, 5, 8, since it's not divisible by 2. Increment our count. Our total now becomes 16. Then we divide by 100. So we get 46. And then our count, we increment it to 8. Then our total becomes, what is that? 16 plus 6, so that's 22. And then 22. So then we divide this by 100 since 6 is divisible by 2. So this becomes 0, and so we don't iterate anymore. So we should have been keeping track up here, but this all increases our iterations up here too. So iterations becomes 8, and our total becomes 17 plus 22, so 19 plus 20, which is of course just 39. Alrighty. So now iterations mod 4, while y, that is still equal to 0. So now this is just going to be 4, 6, 5, 8, 1 again. Right? So, okay, so that means we need to go through this loop yet again. We'll erase all of our numbers here. So we get 4, 6, 5, 8, 1. So then we do our count, which is going to be 8, and our total starts out at 0. So then we increment our count. We increment our count to 9, and then we divide by we increase our total by the last digit, so that's 1. And then we get 4, 6, 5, 8, just divided by 10. Then we increment our count, add the last digit, and then this time we divide by 100, so we get 46. So then we increment our count, then we add the last digit to get 15, and then we divide by 100 since 6 is divisible by 2, so then we get 0, and then we stop. So then that means our iterations increased up to 11, and then our total increased up to 54, I believe, 54. So then iterations mod 4 this time, that's going to be 3. So then we do 3 plus 4. So now we have to do, why am I doing plus 4? Plus 1. So then we get 10 to the 4th. So we're dividing this by 10 to the 4th, which is just 4 zeros, like that. So that basically means that we have to take off 4 digits here. So we take off 1, 2, 3, 4. So this just becomes 4. So this final loop, this will be much, much easier. This is still greater than 0, so we pass it in. So then we get 4. We increment, or we don't increment, our count is 11, and our total is 0. So then we increment our count up to 12, and then our total is the last digit, which is just 4. And then we divide it by, I guess, 100, but that's just 0. So then we stop that loop. We bring it up here. Our total increments up to 58. Our iterations is now 12. And then we do 4 divided by 10. This time it's 10 to the 1st, because 12 mod 4 is 0, so 10 to the 1st. And so this is going to be 0. And so this loop is finally going to stop, because now this condition is no longer true. So we finally found the end of it, so that means total is going to be 58. And then that means our iterations here is going to be 12, because if we look back on that last question here, we had iterations of 12. So that means iterations is 12 for number 29. So if you're just joining us for 29, just go back and watch 28 to see how we got iterations of 12. Alrighty, number 30. Which of the following is the output generated by the print statement in this program? Alright, so factorial, that usually means we're dealing with some sort of recursion. And it does indeed look like we have our recursive calls, because these are both recursion. So let's take a look at how this is going to work. So our first call is going to have a 7, a 2, and a 5 for n, a, and b respectively. So let's write out our first call. So we're just going to represent a function call with like calc or something. I don't want to write factorial every time. So we're calling calc 7 to 5. So if we go into it, we'll see that 7 is greater than 1. So then we go into here. And then, so basically, if n is greater than 1, then we go into here with both our recursive calls, right? Otherwise, we're going to return fact. So that means n is greater than 1 is our base case. So once n is equal to 1, then we stop the recursion. So we'll pay attention to that. We can use that to our advantage. So then we check, is n greater than a, and n is less than b. So it basically is n in the range of a and b. And in this case, it's not, because it's not less than b. So that means we go into our else here. So now we call calc fact, calc, and now we do n minus 1. So we do 6, and then we're just going to do a and b. So 2 and 5. So if this is true, or not if this is true, when this returns, it's just going to return and store it into fact, which gets returned by this. Okay, so now we go into this next recursive call. So we get 6, 2, 5. 6 is still greater than 1. 6 is not between 2 and 5, so we go into the same thing down here. So that means that we're going to have another recursive call of fact is going to be 5, 2, and 5. But now we finally have a recursive call, now we have something that finally makes this true, because we're still greater than 1 here, but 5 is within 2 and 5, inclusive on both sides. So that means that we're going to call this expression right here. So now we're going to call calc is 4, 2, 5, but this time when we're going back up the chain, we multiply this, whatever the result is, we will multiply it by n, and n in this case was 5, right? So we'll multiply the result of this function call by 5. So then in calc 4, 2, 5, 4 is still greater than 1, and 4 is between 2 and 5. So we're going to have the same thing happen, where we have this new recursive call of calc 3, 2, 5, but when it returns, it's going to multiply times the old value of n, which was 4. So all of these ones up here are just going to return fact back up the chain. But this time, this one is going to multiply it by 4. The next one's going to multiply it by 5. So then we'll do 3, 2, 5. 3 is still greater than 1, and 3 is between 2 and 5. So it means we have yet another call, and we're still on this line right here. So we have another call of calc 2, 2, 5. And this time when we go back up, we're going to multiply times 3. Whoops. And then, so then we'll do another recursive call, we'll check this out. So 2 is greater than 1, and then 2 is between a and b. So then we have yet another recursive call of calc 1, can't write down there. We'll just go off to the side. We'll do calc 1, 2, 5. And since we were in this one right here, right, that means that when this returns, we have to multiply it by n. And n in this case was just 2, so we multiply it times 2. And so we finally found our base case, right? Because we have 1, n greater than 1. 1 is not greater than 1, so we just return fact. And fact in this case is 1. So we return 1 from this function. So this function returns 1, right? And so we know that this red arrow represents the return, and we have to multiply it times 2. So we're doing 1 times 2. So that means that the return of this function right here, of this one, is going to be 2. So then we're doing 2 times 3, right? So then that's going to be 6. So the value of this function is 6. And then so we return a 6 from that function back up. So we'll do 6 times 4 now. So 6 times 4 is 24. So this is going to be 24. And then we return it back through, and we do 24 times 5, which is 120. And then we return 120 up the chain, but this time we're not multiplying by n at all. So we're just basically returning 120. And then we finally got back up to our first recursive call. And so we have our value of 120, which is in fact our correct answer for this question. So it's kind of challenging, but this actually does calculate the factorial. You can't always take their word that it's going to calculate exactly what it does, but if you do 5 factorial, I guess we didn't know exactly what the factorial was that it was calculating, but it was calculating 5 factorial, I suppose. So our result is 120. So with these recursive calls, I recommend writing out all of the different function calls like we did here. That way it allows you to better, trace it through the program a little bit easier. Because because it can get kind of hard otherwise to see it. And as long as you write all your work down, then it becomes a little bit easier to trace through. So it's asking us now, in that previous question, in question 30, we calculated this factorial, and it asks how many times is a calc factorial function called. So why don't we look back at our work on question number 30 here. So if we see here, we called it 1, 2, 3, 4, 5, 6, 7 times. So we called it recursively 7 times in the program. So that means that this is going to be 7 for our correct answer for 31. And if you don't know how we call it 7 times, go watch question 30 to see how we did that. All right, number question 32. Which of the following describes the use of selection or repetition constructs within the main function according to course standards? So the first one is the use of a loop for the validation of input given by the user. So that's not necessarily describing our course standards too much, right? Because it's just saying a loop for validation. So that's probably going to be not the correct answer, but let's take a look at our other answers to see. So B, the use of a switch to select the correct printf statement to execute. Oh, I'm sorry, this is, all right, now that I reread the question, this is saying repetitions in the main function. So the main function is what we're primarily dealing with. So in main, we can use loops, but if we're doing the validation of input given by the user, that involves printf and scanf, and neither of those can be occurring in main. So that means that A is more than likely not true. So then B is saying the use of a switch to select the correct printf statement to execute. We can have switch statements in main, but we cannot have printf statements. So if we're selecting printfs, that means we can't do that. So that means B can't happen. C, the use of an if-else to select the correct user-defined function to call. Well, ding, ding, ding. Main should only be doing user-defined function calls, right? We can use if-else's in main per course standards, but they have to be calling functions. So that means C is, in fact, our correct answer for this question. All right. And then question number 33, our final question for this exam here. Which of the following would be considered a good design with respect to the efficiency of instruction execution? So A states that coding the most frequently true logical expressions first in an if-else construct. So this actually is a really good practice to do. So this is going to be a correct answer, but let's take a look as to why it is. So what this is saying is, say we have some, like, I don't know, we have a function here, and it takes in a parameter x, and say x is 1 1,000 times, and it is 2 1 time. So if we run this 1,001 times, 1 is going to happen 1,000 times, and 2 is going to happen 1 time. So if we were going to say if x equal 2, then do some code, otherwise do some code. This is not as efficient as it could be, because this x equals 2 is only going to happen 1 time out of 1,001 times. So that means we're going to have to do this and this the majority of the times. But if we did x equals 1 and we just flipped it, then this is much better, because this is only going to execute this line 1,000 times, and then the one time that it is equal to 2, then we have to do the extra step of going to the else. So usually the things that are going to be the most often, you want to have earlier on in your if-else. That way it doesn't have to go too far down the if-elses. So that means A is our correct answer, but let's take a look at the other ones. All right, B, using a for loop rather than a while loop when a pretest construct is necessary. All right, this is a really weird one. I've never even heard of like a pretest construct before, but I kind of what I think of what this is talking about is like say we had the while loop while x is greater than 2. This would be a pretest. A pretest construct is something that like we need to check before we enter into the while loop, and so it would be better to use a while loop to do this, because if we were to do a for loop for the same thing, where we have like an integer up here, this isn't going to work for us, right? Because we initialized this to 0, or we initialized this to some value before, so then when we check it, we're reinitializing it. So if we needed to check, I feel like this would be probably better, like and y is greater than 2, something like that. So say y up here is like, we need to check if that is true before we enter into a loop. If we were to do that with a for loop, it would be kind of impossible, because we'd have to basically do while if x is greater than 2, then do this for loop, right, like this. Whereas in a while loop, we could just include it in both of them, So I think that's what it's referring to with a pretest construct. So that's not efficient because it's easier just to use a while loop where we can just do it in one line as opposed to 2 lines. So I think that's why this one is not true. And then C, implementing consecutive if constructs rather than making use of if-else construct. So yeah, it's usually better not to do this, so this is false. Instead of having a bunch of ifs like this, you should definitely be using if-elses. So it should always just be if-else, stuff like that. So that's why this one's false. This one is hard, even though, or it's especially hard because this is only useful if you're using like multiple returns, but you're not allowed to do that. So basically, you should always try and use if-else, else-if, use the else and else-ifs rather than just making a bunch of if statements instead. So A is certainly the most correct one. B is kind of a weird one, but it's false. So A is our correct answer. And that makes this the end of this exam. So hopefully this was helpful. If you have any questions, please leave them in the comments. And thanks for watching.